Hi Year 11 Extension 1 Mathematics students. Today we're continuing on with the topic of polynomials and we're learning about multiple roots. So if the function fx equals x plus 2 all squared, we say that the quadratic equation fx equals 0 has a double root at x equals negative 2, since there are two equal roots. So this is when it has a double root at x equals negative 2, it means it bounces off the point at that point, and it has a turning point. So if fx equals x minus 1 all cubed, the cubic equation fx equals 0 has a triple root at x equals 1. So notice there is always a turning point or a point of inflection where there is a multiple root. So in this case, it is a point of inflection when there's a triple root at x equals 1, and that's where the point of inflection is. So if our polynomial px equals x minus k all squared times qx, then px equals a double root at x equals k, which means it has two equal roots. So that's when it's a quadratic. If px equals x minus k cubed times qx, then px equals 0 has a triple root at x equals k, which is when it has three equal roots. And then if px equals x minus k to the power of r qx, then px equals 0 has a multiple root at x equals k, and so it has r equal roots. So we can also say that px has a root with multiplicity at r at k, x equals k. Let's have a look at some examples. For the polynomial px equals x plus 2 all squared times x minus 1, we want to first examine the behaviour of the polynomial close to its multiple root and describe how this affects its graph of this root. So for our polynomial px equals x plus 2 all squared times x minus 1, it has a double root due to the squared here, and so it has a double root at x equals negative 2. And so we want to look at the sign of px close to x equals negative 2. So we're going to do on the left-hand side of x equals negative 2 and on the right-hand side of x equals negative 2. So one less and one greater. So we're going to let x equal negative 2.1, and we're going to substitute that into our polynomial. So negative 2.1 plus 2 all squared times negative 2.1 minus 1. And when we put that into our calculator, we get negative 0.031, which is less than 0. So this means that the curve is below the x-axis. And then we're going to let x equal negative 1.9, so that's just bigger. So when we sub that into our equation, or into our polynomial even, so we've got negative 1.9 plus 2 all squared times negative 1.9 minus 1. That equals negative 0.029, which is less than 0. So the curve is also below the x-axis as well. Looking at part B, we want to describe the limiting behaviour of the polynomial. So our polynomial px equals x plus 2 all squared times x minus 1 has our leading term, if we were to expand it, of x cubed. So it has an odd degree. And a positive leading coefficient. So as x approaches infinity, our polynomial will also approach infinity. And since px is odd, as x approaches negative, Siri wanted to get in the conversation, px approaches negative infinity. So if we were to sketch this, so for our polynomial of px equals x plus 2 all squared x minus 1, we have our x-intercept by let y equal 0. So 0 equals x plus 2 all squared x minus 1. So therefore x-intercept will be at negative 2 and 1. And then we have a y-intercept. Let x equal 0. So we have y equals 0 plus 2 squared times 0 minus 1. So 0 plus 2 squared times 0 minus 1 equals y-intercept of negative 4. So if we were to sketch this, we have our negative 2 here. We have our 1 here. Negative 4. And so when we were to sketch it, we know that it starts, because it is odd, it is going to start and end at different points. And also because it's odd, it is going to start down the bottom because it's got a positive coefficient. It's got a turning point at minus 2, goes through negative 4, up through 1, and then continues up. I'm just going to tidy that up a little bit. Add our arrows, and we write that we have px equals x plus 2 all squared times x minus 1. So then we have turning points at multiple roots on polynomial graphs. So if the multiplicity r of a root is even, there is a maximum or minimum turning point at the multiple root. If the multiplicity of r root is odd, there is a point of inflection at the multiple root. So we want to sketch the graph of px equals negative x, bracket x minus 3 all cubed. So this has roots. So px, oops, that's too thick. Px has roots at x equals 0 and x equals 3. So they're our x-intercepts of 0 and 1, 2, 3. And then it has x equals 0 is a single root because there's no power to that x. So at our negative x here, that gives us our root of x equals 0. And because there's no power, it means it's a single root. Whereas at x equals 3 is a triple root. So that is from here because it has a cubed on it. So this means So therefore at x equals 3, there is a point of inflection. The degree of this is going to be even, because our leading term is negative x to the power of 4. So therefore our px has even degree. So that means that our graph wants to be either both endpoints facing up or both endpoints facing down. Even degree, but it has a negative leading coefficient. So we want to have both our endpoints facing down. So that means that we're going to start down here as we go through our 0. And then we have a point of inflection. So we go up. And then we have a point of inflection as we go through 3. So that is what our curve looks like. And we should write that it's px equals negative x times x minus 3 cubed.